Thanks everyone for joining. Our goal today is to build a global AI model for rare brain lesions. We'll just need you to send us your imaging data. And
No, that may violate our GDPR as stated.
Our legal office is at lunch.
Yeah.
For a while.
Data cannot leave our institution.
Same here, Miyave.
Actually speak and data can't walk.
Moving patients can't. That's too spicy.
wait, please. No worries. I get it. I totally understand. We can use federated learning instead.
What's federated learning?
Yeah, federated learning what?
Let's ask Bender, he's our expert.
Hello, team! Federated Learning lets us train one model together while keeping all patient data inside each hospital. Here's the loop. First, we send a base model to every site. Second, each site trains locally on its own scans. Third, sites send back model updates. Just numbers like weights or gradients, not images. Fourth, a coordinator aggregates those updates into a better global model and sends it back out. We repeat this cycle until the model is ready.
Do we need a central server for that?
Yeah, pro, cons.
In healthcare, the most common choice is centralized coordination. A server orchestrates rounds, collects updates, and computes the aggregated updates. It's operationally simple, easier to monitor and audit, but it is a single trust and failure point. There's also decentralized, peer-to-peer FL. Sites exchange updates with neighbors, for example in a ring or gossip pattern, and repeatedly average with those neighbors. Over time, the network converges toward a shared model without a single boss. That design removes a central point of trust and can be more resilient, but it's harder to secure, audit, and tune, and usually requires more communication.
Centralized sounds appropriate for our governance.
Technically, our updates combined.
The default combiner is federated averaging, or FedAvg. It's a data-weighted average. If Site K trained on N samples and produced its own weights W, the server computes a weighted average as new global updated weights.
Any alternatives if we worry about bad updates?
Yes, we can use robust aggregators like the coordinate-wise median, the trimmed mean, or algorithms such as Crumb or FL Trust to reduce the influence of poisoned or outlier updates. And for steadier or faster global steps, we use server optimizers like FedAtom, FedAdigrad, or FedYogi. There isn't a single winner. FedAverage remains the baseline, and we adjust when the data demands it.
Hospital differ. Can the model adapt per site?
Yes, we often keep some layers global and let others stay local. In practice, the shared backbone, for example, convolutional or transformer blocks, is averaged globally so everyone benefits from collective signal. Meanwhile, we keep batch norm statistics local, and we allow small adapters or the final classification head to remain local. This gives us a strong shared representation, plus site-specific tuning, where local data and protocols matter most.
Our scanners and protocol differ. How does that affect training?
That's the reality of non-IID data. Differences in scanners, protocols, demographics, or labeling policies can destabilize training and hurt some sites. We address this with data-weighted aggregation, as explained in FedAvg, so small sites don't steer the model, or via proximal or variance reduction methods to reduce drift. Proximal terms keep clients near the global model, while variance reduction sends corrections that cancel drifts. There is also self- or semi-supervised federated learning to leverage unlabeled data, as well as domain adaptation or site-aware normalization, so the model absorbs distribution shifts. When training fluctuates because sites differ, use data-weighted averaging and proximal or variance reduction to keep updates aligned and reduce drift. When the model underperforms across domains, use self- or semi-supervised FL to mine unlabeled signal and domain adaptation or site-aware norms to align distributions. First, keep optimization stable, then make representations transferable.
Can the server see my hospital's update?
With secure aggregation, the answer is no. Each site cryptographically masks its update. Those masks are designed to cancel out only when all masked updates are added together. The server can recover only the aggregate, for example the sum or average, once a minimum number of sites have contributed. No individual update is revealed.
Are there strong privacy guarantees?
What we give up?
We can add differential privacy at the client or the server. That means we add calibrated noise to updates so an individual patient's contribution cannot be inferred. Privacy is tunable. Stronger privacy typically costs some accuracy. Moderate noise often strikes a good balance.
How do we prove the model works without sending predictions?
We run a federated holdout. Each hospital evaluates the trained model on its local test set and returns metrics only. For example, DICE, AUC, calibration curves, and others metrics of interest. This approach is safer than shipping predictions.
Where does this help the most?
Federated learning shines in rare diseases where each hospital has only a small cohort, in segmentation and classification across multiple vendors and countries, in computational pathology, where massive whole slide images stay on-prem, and in survival or longitudinal analyses, where cohorts remain distributed, but the model is shared.
So if you can run our client on site, you keep your data, and we all share the learning.
Yeah, let's build this together.
Federated learning. One model, many hospitals, zero data movement.
Okay, so what do we name the model?
Neuro curry. Very tasty.
Ahí, picante. Give it some kick.
I propose some names that embodies harmony and grooves. I will share the characters.
FL Clinical B 2025 Final Beta.
No, guys. Let's do the Italian way.
Bellamente.
We should call it Anastasia.
No.
No.